Okay. Good night, everyone. Good night, everyone. Welcome to another workshop. We have two more workshops lined up for you, and I trust that you guys actually we're halfway there actually, because we've done two workshops before on AI, and we're at the middle part. So I hope you guys are ready for another exciting adventure as we uncover some AI tools and see how best we can utilize AI solutions in building or different software projects, etc. All right. So welcome one and all. We're happy to have you. Now, we are Jamaican developers, and we are looking into building and marketing each and every one of our skills, learning and growing together, joining this space, ensuring that you get an opportunity to share knowledge and also learn from other persons in the industry. And this is essentially who we are and what we're about. So definitely, if it is that you are not a part of the community, or if it is that you have some friends that would be interested in joining the community, feel free to join. We have many communities in the Jamaican space, and we're of course expanding. So wherever it is that you best fit, feel free to join, whether it is our Flutter community, whether it is Jamaican developers community, whether it is the Jamaica Artificial Intelligence Association. We have something geared for every and anyone who is in the field of computing. All right, so this will be our agenda. So the next event is going to be September 12th, and we'll be looking at advanced image processing. And our speaker for that event is actually going to be Kevante Brown. All right. And following that, we actually, as we said, we've been doing these workshops in preparation for our UA hackathon, which is going to be held September 23rd. So please be on the lookout. All right. We'll be going into today's presentation, where we'd allow Dimitri to shed some light on the AI information that he has. Just a second. And of course, we will go into our question and answer section, which allows you guys to write your questions, interact with Dimitri, maybe get some more knowledge as it relates to some of the things that he has explained. All right, so here is Dimitri. He's already online, and I'm sure he's ready to share his knowledge. Now, he is a Bachelor's of Science in computer science. He has a Bachelor's of Science. He's a software engineer, and he will be looking at machine learning algorithms. Okay, so this is one of the areas of computing we would have looked in AI. Would have looked at how it is that we can use AI to detect image and classify them. So here is Dimitri, who's going to be diving a little further in AI. All right, I'm going to now hand over to you, Dimitri.
Thank you. Yes, guys. So as I said before, I'm a software engineer like you guys. I've been interested in AI from as far back as 2018. So the purpose of this, I hope, is to show you guys around the field basically and give you guys an idea of what to expect. And if you are interested in any way in pursuing anything in machine learning, I'm hoping to guide you in a correct path basically. Yeah. So I'm going to share my screen and let's get started. That's what you guys are seeing. So, the name of the presentation today is called Hugging Face the new GitHub for AI because spoiler guys, that's basically what it is. We have AI, this new emerging field, and we kind of need a website that kind of brings things together and makes things easier to process this. So let's start off with Hugging Face. What is Hugging Face? What are our objectives? What is Hugging Face? What's it for? We're going to look at some examples of what we can do to help Hugging Face, and I want to also learn some fundamentals. What you want to know before using it, right? Okay. So what is it? Hugging Face is a platform with over 120K models and 20K datasets and 50K demo apps, basically spaces. That's what they call Hugging Face, right? We'll get into what all that means before this is over, right? It's all open source and it's all public. It's not all open source. It's mostly open source and it's all publicly available for you guys to just click on to, just move your screen, type it in to Google and click on to everything, and you can see everything yourself, right? So you can easily collaborate and share stuff and build ML together using the Hugging Face Hub here. And works as a central place for anyone can explore and experiment and collaborate to build machine learning technology, right? So it's becoming very important right now in the machine learning space, this Hugging Face thing. It's really something you should know about. If you're not using it, you're really not taking advantage of all the options, right? So let's have a look now at the Hugging Face. So we're just gonna click on it and kind of just have a look around first. So this guy is basically your Hugging Face Hub. So if you notice up at the top here, we have models, datasets, spaces. That's because of three reasons. The three most important things you need in any machine learning projects is the model itself, the dataset, and of course the compute, which we have represented right here by spaces, right? Over here we have profile, a number of things that we can get into. But the most important thing right here is essentially learn. If we go into this learn thing over here, we see have a number of courses, NLP courses, deep RL courses, audio courses. So you can actually learn a lot. I actually recommend this information right here. You can actually learn a whole lot about machine learning from Hugging Face. So I would recommend it though for the beginning. You want to kind of get into machine learning a bit first. You want to learn what a machine learning model is, build a first classifier, and then know what NLP is before you want to jump into this. Yeah. So after that, I can recommend this for anybody to start jumping and learning all of it. Right? So also, let's have a look up here at how we can do on a search, right? So for example, let's say I wanted to have a look at image generation model, Stability AI. They're at the top right here for image generation. So Stability AI, Stable Diffusion. I'm sure you guys have probably heard of that. That's the image generation model right here. So you can actually go onto here. They have like a page and all of the extra info that they need to learn about the performance, comparing it, how to install it. Some of the basic code you need to just run it on a notebook or something like that, and we'll get into notebooks further on. Some basic Python code I need to get into Hugging Face Hub and in one of these models. So it's basically the same thing for anything you want to do. Like say, for example, you know the llama command models are very important. So say we want to do Facebook llama. Oh wait, or is it Meta? Yeah, Meta llama. Meta llama. Of course, they have their whole thing over here. So you can scroll up and see all the information about llama. They have the different versions: 7B, 13B, 70B. And one thing that we'll see is that the performance of these models kind of scale along with the size. That's bad in other ways, but at least it works basically. So, we also want to have a look here at the data sets, right? So data sets are extremely important for machine learning. Oh, this kind of, okay, that's good. All right. So data sets are very important for machine learning, and this is why Hugging Face Hub is so important. It basically collects all of the important data sets, 61,000 data sets. That's a whole lot of data, and makes them extremely accessible. So whatever type of task you're working on, this can usually be of some help when training the models, right? And have different types of tasks as well. Also, I want to talk about the Open LLM board basically, right? So this is the benchmark board for the leaderboard, basically for the machine learning models for LLMs. So right now we can see where Meta Llama 7B is on top, Llama 65B, Hugging Llama 65B, Llama 30B, 13B, 40B. So you can see like we have a correlation right there in terms of performance of the model and the size of the model. It's directly correlated. And we're going to get more into that later. Oh yeah, and of course there are different types of models. I really selected out the pre-trained models. So you have your best fine-tuned models. This page moves a bit slow. Yeah, and I can select for what you want. So we have these things right here: the fine-tuned, instruction-tuned, RL-tuned. If you don't know what it is, you're probably gonna get into that at some point. So the instruction-tuned is the kind of question answering ones, and fine-tuned is basically for any type of different language tasks can come up with. I have those type of models as well. And of course, I have a Hugging Face spaces, but we'll get into spaces later on. They're pretty important. Okay, and of course, I can provide your own profile, the stuff on there for that. And of course, there's also guides on how to use it, settings and stuff like that. But let's move on now back to presentation. Presentation. Okay. Hugging Face Up. That was Hugging Face Up. That was the intro for the Hugging Face Up. So what else we want to see now? So that's good. So let's start off with the task of causal language modeling. So we need to talk about this before we can get into anything deep learning when it comes to language modeling. Basically, we want to start basically at the beginning. So when I start looking at the code, you guys can kind of get an idea from where I'm coming from, right? So what is this task of causal language modeling? There are two main ways to train LLM models. That's causal language modeling and also mass language modeling. Causal language modeling is also called autoregressive modeling, and it basically means predicting the next word in a sequence. So given a sequence of words, hello there, my name is, it basically it will predict the most likely next word. So the sky is, and the next word that what it will predict is blue. So it's very similar to, well, we'll get into it. Another thing, this is the mass language modeling, right? So mass language modeling is basically the same task, but instead of predicting the word at the end, we're predicting the word randomly from in between the sentence. So that's the only difference that causal language modeling has to do with mass language modeling. And also that's, of course, causal language modeling is of course what we do with GPT in the pre-training stage. We'll get into that more. So some notes about causal language modeling. Of course, went over this. The task of causal language modeling is the task of predicting the token following a sequence of tokens. In this situation, the model only attend to left context. That means to say, just as we saw a while ago, it only pays attention to the first half of the word, the first section of the word, basically, and it's not able to see the last part of the word. It's part of the sentence, so it's able to predict that, right? So it looks at the first part of the sentence and predicts the rest of the sentence. So the GPT formula uses the GPT formula models use the causal language modeling in pre-training. BERT is an example of a large language model that uses mass language modeling as a pre-training step, right? This is only done in pre-training, right? The only train model with causal language modeling is as a pre-training step. We don't really train it as a fine-tuning step, but it's kind of not the purpose of the model in itself. It's always a fine-tuning step after the causal language modeling step, because causal language modeling itself, which is just predicting the next token, is not in and of itself a very useful task to perform. Right? So I have to fine-tune it first before you can get to that. And causal language modeling is analogous to the keyboard, basically. So stuff on the keyboard, like over here, you will type in great, and the keyboard will predict the next most likely word. Great time, lovely time. I had such a great time, lovely time. So that's the same thing that causal language modeling is doing. It's producing like a probability map across all of the words in the English dictionary for the most likely next word to come after that, right? So you input as a number of sentences, a number of words, and after that it outputs a probability over every single word in the English dictionary of what is the most likely answer. So it's also it's also similar to classification, text classification, right? You can consider it a form of classification where the input is number of words, and then output is the classification of the final word, the next word in the sentence. So it's kind of a classification. You can think of it as a classification task. So just like how we have image classification up here. So for image classification, you usually have the image going in here in the front part of the model, and as the output of the model, we have a number of probabilities as to what is the most likely thing that's in the image. So similar to this, we'll have the first part of the sentence going in here and have a probability map over here of what is the most likely next word in the sentence, right? And we do a calculation on that and say, okay, sky is blue. So I hope you guys are following along, right? So if you know about convolutional neural networks, and of course we'll get into that more next week. So if you don't understand that, we'll be seeing more of that, of course. Yeah. So for NLP though, we're not doing CNNs today, we're doing NLP. So transformers are basically the most important thing in NLP. For now, and probably for a good while to come, right? So they're used for processing sequential data. What means sequential data? What means stuff in a list. So anytime you have something that's coming after another thing, for example, you could cut up a picture into slices, and you could turn it into a sequence. Of course, words are sequences, letters are sequences, audio is a sequence, audio is actually a list of numbers, right? For example, financial information, so like stats data, that's a sequence. That's a good example of what you could use a transformer to process, right? The transformers were released in 2017, but then nobody really knew the potential for these things. So Google kind of just released it as regular research, and people built on top of it until because the revolution in deep learning that we're seeing today, right? Yeah, and of course it kicked off the current AI LLM paradigm, right? Large language models are entirely happening now, enter existence to transformers, right? And we have a few advantages to transformers because, of course, people were trying for many years before 2017 to actually do the same things that we're doing today, right? But it wasn't working because of a number of reasons. First of all, the most advanced technology at the time was RNNs. RNNs have a number of issues. They're slow because they don't process things in parallel, right? So they can't actually take advantage of the speed up that normally have in deep learning that would come from using GPU, which is parallel processing. So RNNs are actually incapable of taking advantage of that. So right, even if RNN could do what a transformer is doing right now, it would take it way more time and way more compute actually do that. So that's why transformers are superior to RNNs. That's one of the reasons. And they also have a much longer context then. That means they can essentially fit more into a transformer than they can fit into RNN. And they don't suffer from what we call the vanishing gradients problem, right? Well, they suffer from something else, but vanishing gradients problem was really an issue when it comes to RNNs, right? So for example, it starts to forget earlier words in the sequence when it reaches later words in the sequence. So it places more importance on the later words in any given sentence than the earlier words in a given sentence. Yeah, so this problem of context length is very important, and we'll be coming back to it. So this over here is the basic diagram of our transformer. So here we have the input embeddings. This is the encoder, and over here we have the decoder. So this is a very common design for any type of machine learning. So you have encoding and decoding. Encoding essentially means that you are turning the words into a format that is readable by the machine. And then decoding means that you're kind of turning it back into something that's readable by humans. So that's what we're doing with encoding and decoding, right? So we're transforming a sequence of words into another sequence of words. And that's what transformers kind of do. They kind of turn one input of numbers to another output of numbers, and these numbers are just in sequences. Like seriously, guys, this is fundamental to understand about machine learning models. It's just a function, a mathematical function, or a programming function that you guys work with every day that takes in a bunch of numbers and spits out a bunch of numbers. That's all, right? So that's why you kind of can't expect certain things out of it because yet it's just a function. It doesn't have certain capabilities like us humans. It has a limited amount of inputs. Okay, we're gonna get back to that when we talk about the context. So let's talk about the context. So in the realm of LLMs, the context length refers to the number of tokens or words that the model takes in to account for when making predictions, right? So that's basically, say the maximum, imagine for example, the maximum amount of tokens that we could take in is say 20, maybe you could fit in this sentence right here. Say about 20 words in the sentence, probably less. All right. So that's the context then. And it's very important that you understand this. I'm going to go over it multiple times just so you guys can understand. The context then is very important. It's the main limiting factor of what current day transformers can do, right? And if nobody solves this, it solves this issue that we're having with a limited context length in these models. It's going to be a while before we actually get where we need to be or where we want to be with artificial intelligence in general. It's a main limiting factor in the designer artificial intelligence systems. They have a limited scope of input. They can only see as much as basically they are presented with. Imagine if you could perceive the world and all you could remember was what you're currently seeing. So that's RNNs. That's transformers. They cannot perceive more than what they're currently seeing. So for example, when you're using GPT, everything that you type in GPT have to fit within the context. After a while, if it's not fitting inside the context, it actually gets truncated or moved. So the model actually cannot pay attention to all the text in the sentence, right? So all the parts of the conversation completely get forgotten after a while. We have ways of going around it. There are all workarounds. There is no actual solution to the issue of limited context length. The context length is pretty large. So for example, you have around standard is around 4,096 tokens for models, right? But if you try to get above that, you tend to have to use a bunch of extra things, a bunch of workarounds, a bunch of extra methods, and none of them really perform all that well. But you know, people are still trying. There's plenty of research to do, and I'm sure a lot of people are having a lot of fun trying to fix this issue of limited context length. But I don't think just increasing the context length is what you need to do, because that's not really how humans perceive, right? We don't see something now and then completely forget about it. We don't really have to perceive every single thing, right? We can have memory, and that's really the part that LLMs lack. They don't really have memory in the way that we perceive. It's just that they have perception and they have what they learned in training. So if it's not inside the training, then they're really not going to remember it. If it wasn't inside the training and it's not inside the context, there's absolutely no way the language model can consider it. So they can't remember something they did yesterday unless it's in the context. Okay. So before we get into any more LLMs, there are a number of things in the code. There are a number of things that we have to go over first, right? So first, I'm gonna go over tokenization. What is tokenization? It's gonna seem pretty obvious, right? So LLMs, artificial intelligence models in general, cannot handle text, right? Text makes no sense to them, right? Because their functions, they only can make sense of numbers. Because they're doing calculations on those numbers, they can't do calculations on text, right? So have to find some kind of way to input text into the model. We'll have to convert it to numbers first, and that is where tokenization comes in. So tokens are the basic units for text code that the LLM AI uses to process and generate language, right? Tokens can be characters, words, subwords, or segments of text or code, depending on the chosen tokenization method or scheme. Tokens are assigned numerical values, are identified, and are fed into the output, fed our input into the model, right? I finished with the tokenization. So as we can see here, right? This is a text input, for example. This is the text that would start with, right? This is what you would type into ChatGPT. First of all, before we can even put it into the model, we need to turn it into numbers, right? So the first step of turning it into numbers is actually just turning it into numbers. But what we use for this is a function, a one-pin function called tokenizer. So for GPT specifically, right? It uses subword tokenization. And what this does is it splits words into parts. Sometimes parts, I'm not always parts, but basically it does it in a way that every single word in the English language can be input into the model, right? And we have to have this start token and this end token right here. So as I said, it's a list, and it's still a list even when we convert it back into numbers and this is still not what we're going to put in the model. What we put in the model is actually what we call embeddings. So these numbers get mapped onto another set of numbers called embeddings. And these numbers are very high dimensional vectors. And let's get into that. What are embeddings? Word embedding is an AI technique for representing words and sentences in a very large vector space, right? So we need to do this in order for the language, in order for the models to make sense of the words, right? So what's happening is that you would think that just saying, okay, just say the word, just say this word is associated with this number, and this word is associated with this number, and this word is associated with this number, and you could of course fit this into the model, right? But it turns out, as it turns out, the model actually isn't able to make sense of these simple representations of the words, right? So what we actually have to do is represent the words while actually putting the meanings of the words into the representation itself. And that's where embeddings come in, right? Embeddings are what we call high dimensional vectors. High dimensional vector sounds very fancy, but it's really not something you're not familiar with. It's really just a list of numbers, specifically floating point numbers. You guys are all familiar with that, right? And these are what we use to represent words, right? So they're able to capture the meanings of words in a computationally compatible way. So what we'll see, right, is that the embeddings, they kind of represent words in what we call a high dimensional vector space. So each word has a set of numbers that's associated with it, and each other word is actually related to that number, to that word in a numerical way. They can actually calculate the distances between words and stuff like that. The distance between words, the space between words, the meanings of certain words grouped together, words that are close together have similar meaning. For example, man and woman, you might see that it's at a similar place inside the vector space. What I mean by a vector space now is a very high dimensional vector space, but you can actually start imagining what a vector space is by imagining 3 dimensions, right? And it's a single point, a word is a single point in a vector space. And you can actually, with embeddings, you can do calculations on the words to actually get different words. For example, if you subtract the vector for woman from man, you actually get you actually get the word queen, exactly, for example, right? Man from man, king. You know, some type of calculation right there. Subtraction, and move over to another vector that's actually similar in meaning. So it sounds kind of magical, but it's all mathematics, right? So continuing word embeddings. So we know that the word distances carry meaning, and typically we use hundreds of numbers to represent the meanings of the words, right? Hundreds of numbers and thousands of numbers inside of one list to represent the meaning of one single word. So the word okay. Hundreds and thousands, thousands of numbers are used to represent that word. And actually we find that the more words we use, the more numbers we use to represent the word, the more accurate the model can be, basically. And this is bad for a lot of reasons, but at least it works. And also, the next thing that we have to get into is attention, right? Attention is actually the most important part of the transformer architecture that we just saw before. I didn't go over it in a bit. Should I go over it? Huh? So attention is basically this way of processing sequences, right? So what it allows the model to do is relate things that aren't necessarily are different parts of the sequence, and actually get an idea of which one of those things are important. So example, we have a sentence right here, and we're relating it to other words in the sentence. So we produce every attention layer produces what we call an attention score inside the model, right? And it kind of give you the model an idea of what words are most important for deciphering the meaning of the sentence, and then creating an output. So I have different types of attention. I have cross attention, self attention. But we're not gonna get into those. I'm not gonna get too much into that because that's really in terms of model architecture. So for today, we're just gonna look at what attention means, and I'm hoping you guys have kind of give you guys an idea what I mean by attention. So this is a very good way of thinking about attention. So for example, right here, we can turn, as I said before, we can turn images into sequences, and then we can feed those into the same neural network models that would feed languages, and they can apply attention scores across the image, just as we would have it across a sentence, right? And if you notice right here, right, we have the original image of a bird, we have the attention mask, and then we have the map, attention map over the word itself, right? And if you notice, the parts that are highlighted in this attention map are the parts that you yourself would be looking at if you're looking at this image, right? So this is what you are focusing on in this image, and you notice that the attention mask is actually focusing on the same thing that you would be looking at, right? So that's actually seems a bit obvious, but to neural network models, it's not necessarily obvious, right? They don't have this idea, well, okay, this part of the image is more important, this part of the image, and this is less important. That's actually very fundamental for why neural networks and language models can work, right? So let's get into a demo now of how we can train a causal language model and how we're going to use Hugging Face to do it, right? Hugging Face kind of makes all of this very possible, very easy. Without it, you know, it would be a lot of code, a lot of boilerplate stuff that you have to figure out yourself. But let's not go there. So let's go here first, guys. Or not. So this is Google Colab. We're gonna just look at some code for what you would typically do when you're trying to run an attention LLM or any type of neural network model. So this should be probably very familiar looking to you if you've actually been in AI for a while, right? So what we're doing up here, basically just your regular installs, your pip install and stuff. If you're from JavaScript, you probably know this as what equivalent of pip again? NPM install, right? So we'll just install a number of packages right here over here before we can get to anything. So we have a number of important packages. Dataset is one that comes from Hugging Face. Transformers is actually the most important one that comes from Hugging Face. Accelerate is also a very important one. This helps to speed up all our processing. What this one is about. But yeah, evaluate is one that we're not going to use right now, but it's here because it's there. So first thing we need to do, we have to get a password from Hugging Face because we're going to use their service. So you kind of have to use a bit of security right here. So you just run this little code over here and the access token. You would actually just come to your Hugging Face account. So this is when you go on to your profile, right? Settings. And you have a number, for example. So come over here with the settings, right? And I can see access token right here. This is very important. You're gonna just run into this. This is a very basic thing. You just need to solve. You get your Hugging Face token right here. Boom. Copy it and paste it. This is just because we're gonna be using Hugging Face for this model. Pull stuff and push stuff to Hugging Face, right? And then right up here, we're actually setting up some text processing, right? So what this code is doing, we're gonna try to train a causal language model. But before we can even do any of that, we need a lot of text, basically, and that's gonna take up a lot of space. And we need to pre-process it to kind of exclude some things that we don't want from it, right? So any keywords in string, this is kind of a search function. We're gonna be filtering some stuff based on this one right here. And then continuing, we're doing more text processing right here. Filter streaming data set to have a number of for loops right there. And I'm kind of boring stuff. But yeah, we have to filter the code to ensure that what we're processing is actually stuff that we actually want to process. Again, what we're trying to build from here, right, is a causal language model, but we're going to train it from basically code. We're going to actually use a pre-trained model and retrain it to work with code, or like the specify to work with code. Yeah. So, but this is actually still pre-training though, because we're not specifying any actual task that like question and answer or anything like that. So we immediately hit a blocker right here. So or notice this cell will take very long to execute. So you should skip and go to the next one, right? So in reality, guys, we won't be running this notebook today, but let's look at the other stuff that I want to share right here, right? So what's happening here is that it's downloading a bunch of data and it's going to be running through all of these things, right? These filters right here to filter what I want. And this takes quite a while because it's a lot of information. I think it's probably like a couple gigabytes worth of data to process. And then this is data from datasets. We're gonna load datasets and dataset. These are just functions that we use for processing, for pre-processing dataset before we can feed it into the model, right? So this is the raw dataset that we're gonna pull in from here. After that is finished running, like 5 hours from now or something like that. Okay. And this is an example of the text that we're going to input into the model, right? So repo name. So this is basically some text that we're pulling in from Python notebooks similar to this one, right? And what people do a lot in Python notebooks is they use these types of data processing type of tools, right? So NumPy, SciPy is one in one is not very common. We have some information up here, but basically what we want to train the model on is this. I want to train it to predict the next token using this type of information right here. So we're gonna just train it on text processing, right? The next thing I want to show you guys is how the tokens look after they do a bit of conversion, right? So we go from words to tokens, right? So these tokens right here, we're gonna put them into the tokenizer. The tokenizer is a function that we use to convert from text to numbers, which are integers basically. Integers inside of what we call a dictionary that maps every single subword in the English language or any other language to a number of numbers. It's a number, so it's just a map from word to number. And the context length is basically what we're mentioning before, the maximum input of the model, right? I should really be stopping this right now and jumping over to the next one. So this is how we're actually going to run today, guys. So if you notice, it's basically the same thing as up here, but I commented out a bunch of this earlier code that is going to take forever to run. Right? So what we're actually going to do instead is import a bunch of stuff from Google Drive. So I already pre-processed the data, tokenized it. So we have a bunch of numbers already, but I have to import them from Google Drive. That's a very important thing. This is kind of why I like Collab. It's very integrated with Google Drive. And a number of other places, everywhere you go, you're going to find a Collab notebook that has essentially everything that they need. So they've kind of taken over the space as the default provider for this type of service, this default dev environment for running machine learning tasks, basically for testing, basically. But if you want to get serious, you're going to have to use Google Cloud or Amazon AWS services or something like that. But this is an absolutely great starting place, and you can still link this with any of those services, right? V100. Is this V100? I don't think this should be the V100. Just switch it. Oh yeah. Another thing to note, if you guys didn't know about these notebooks. Let's discuss this. Sessions. Is that you have access to a number of GPUs, right? This is very important. You need high-class, high-quality GPUs, not the regular consumer stuff, and that's mainly for one reason, and it's not processing power. It's mainly, well, we have over here GPU RAM. Right? So we don't want this CPU, we don't want to be, well, it can run on the TPU, but really and truly, right now, the best thing to be, it's stated there right now is this A100 GPU. Okay. Right, so it has about 40 gigabytes of VRAM. That's the most. I think this is 16, and this is probably another 16 gigabytes of VRAM. That is the single most important spec when I'm trying to run machine learning models, especially in this modern day of LLMs, which means large language models, which means they are extra large and take up extra amounts of space on the GPU to run. Right? Put that over again. Yeah, guys, and also this is kind of a paid service. If you want access to the A100, which it's not currently, the H100 is currently probably the best GPU you could get, but A100 is still pretty good. It's still pretty state of the art. I mean, it's as you as a consumer wouldn't be able to access anything other than that. And of course, you wouldn't be able to buy one of these. These A100 GPUs are for something like, you know, 7,000 US or something like that. So, care money. Okay, good. So this is gonna take a while to run. So what we're doing right here is we're pulling in some of the same tokens that we're creating in this last notebook that we're going to take forever to create from Google Drive to the local drive. Right? So that's it. We're pulling this zip file that I created earlier. Now what this zip file is basically a bunch of tokenized words, right? So all these words right here. So a bunch of these words right here turns into numbers between 1 and 50,000. And 50,000 because 50,000 is basically 50,000 something is basically the context length, or no, the vocabulary size of GPT-2. GPT-2 is the model that we're going to be using today, right? And it uses subword tokenization. And 52,000 is a good number that actually captures probably all the languages. It's multilingual enough to capture a lot of languages basically. Every single word that you would need to type, right? So you can run over some more of the code, right? So this is after we pull it in, right? We're gonna load it from the disk. Not there yet, still extracting. 30 minutes. Okay. Sorry guys, this is from an early experiment. I should have deleted this. So when we look at this now, we can show in the data set, we're importing it, we'll load it directly from this, right? So this right here is referring to no, it's kind of referring to this right here after we finish extracting it, right? And then we'll see right here, we're seeing features for trained data set, and we're seeing features for validation, right? We're not gonna do any validation today. Well, you're gonna do validation while training, but not really, guys. We're gonna just be doing training. Just gonna worry about these. What is this? 1.6. Oh, this is 16 million rows, 16 million tokens. Yeah, 16 million rows of information is what you would have to train this on, right? Total amount of data that you would have to train. This is just a regular data set. I think this is a subset of an actual data set, like 5% of the actual data set for what you would actually use. And this is 3.7 gigabytes. That is a tiny data set for actually training a large language model. Typically talking about terabytes of data. Okay. Up here we have now the import transformers, auto tokenizer, auto config, auto GPT model. So this is the GPT-2 that we're going to use. Auto config. This is just a configuration for the GPT-2, right? And this is the tokenizer. And so tokenizer right here. We pull it from the GPT-2. But this is actually this is GPT-2, but it's actually where Hugging Face comes in, right? This is a version of GPT-2 that was basically created by Hugging Face courses, because this whole notebook right here is pulled from a Hugging Face courses website. So it's not necessarily my code, guys, but it's fit for purpose for what I'm showing you guys, right? You can always, of course, modify open source code if you need to. So we're seeing right here the config GPT-2. That's the model name, right? That's very important. So basically, if you wanted to support the model right here with something else from Hugging Face Hub, that's literally what you do. If you put in this instead, Llama 7B instead, basically you'll be loading that model instead of this one, instead of GPT-2, right? From featuring. That's what it's called. Good. Can on this now. Can on this. Context length 128, right? What this means is that all that our model will be able to see is a total of 128 tokens. Tokens are actually different from words, but for the sake of simplicity, just consider tokens to be words. Okay. So each token is one word. So what we're printing right here is the config. So you just have basically a whole bunch of stuff that you have to configure for any type of language model. The regular hyperparameters and stuff like that. So for example, we're using a GELU in GPT-2. GELU is a little bit old now, I guess. End of sentence token ID. So that's important. So that would tell the model when to stop. Initialize a range. Yeah, I don't know that one, but you don't need to know every single configuration right here. Model type GPT-2, NCTX. So that's the context. Number of embeddings. That's 768, right? That's a very important number. We'll be getting back to that one, right? Number of heads, right? That's 12 attention heads. That's counting number of attention heads. Inner, no, not even sure what that means. Number of layers, that's 12 layers. So that's 12 total transformers that we have, right? So what we do for improve accuracy when we build in transformers you stack them on top of one another. You have a transformer, at least one other transformer, at least one other transformer, basically. It just spits out information from one transformer to another transformer. Number of positions. So this is, I think the original sequence length or context length of GPT-2 was 1024, but it was reduced in this notebook to actually just make it easier to process basically. Because a larger context length means more compute, more GPU memory. So actually reduce it from 1024 down to 128 for this, right? More stuff is there. You can go through, but let's move on. Transformers, GPT-2 head model. And this is we're pulling in the GPT-2 tokenizer. We're creating the model right here, and we're dropping in the config that we just mentioned up here, in here, right? And then we're gonna have a look at the vocabulary. So if we print the vocab size, we're gonna see this is a very important parameter too. So 50,000, this is the total number of tokens that we actually have in the model, right? No, this is the total number of tokens that the model can actually look at and actually understand. But it captures a very wide range of words, so you don't have to worry about it too much, right? So let's have an actual look at the model. This is how you print the model in PyTorch, right? So this is stuff that you won't not necessarily see other people talking about, right? So this is how the model actually generally looks, right? You're seeing layer on top of layer on top of layer. So you can imagine these as layer, right? And right here it says GPT-2 block times 2, right? And this is a GPT-2 block. Layer 9, attention, conv1d, then I have another one. So this is analogous to the image I was showing you guys earlier of the attention layers, but I guess I didn't go deep enough into it. So this is the embedding layer. This is very important. So the embedding layer, again, remember what I was saying, the embedding layer maps a bunch of tokens to a number of words. So you take in say 128, for example, but so 128 is the context length, basically, but the maximum actual context length is 1024. And we're gonna just pad to 120, pad to 1024, right? So 76 by 768, that is the embedding dimension, right? That is the number. Remember I was saying embedding take up a large number of words actually represented, right? A large number of numbers to actually represent a single word. And these are actually what we're representing with the tokens, right? So right here, this is the first token in the list. Map, you notice it maps to 0, 1, 2, 3. So each one of these numbers gets outputted once you input this word basically, or subword. So these are subwords because of course I start off with every single letter. Then get a bit bigger, and eventually start to recognize the words as actual words, art, right? So not every single word is in it. Some of these you have to just combine words, combine subwords to make words basically. So that is the concept of subwords. Yeah, so you can actually capture every single word if you combine subwords and turn them into words, right? And we have a total of 50,000 something and others, right? Yeah, this just continues up to 50,000. And here's another thing you won't see other people show, right? So tokenizer equal tokens at encode, right? So for example, I wanted to input this text to the model, hello world. First thing that I would do is encode it with the tokenizer. And this is what the hello world look like after you encode it into tokens, right? So tokens are simply integers. And these are between 1 and 50,000. So hello world, translate to that. Instead of said hi world, 31,000 something. We get a different token for hi and hello, right? Let's get the actual look at what embeddings look like, right? So we're going to put this token inside of the transformer, and we're going to look at this layer right here. This layer is relates to this right here. So this is actually inside of the transformer we're actually looking at right now, right? Don't want to let the people show me that. So come at this, boom. This is what an embedding looks like, right? These numbers, these gibberish numbers. You can look at the embedding shape. So it's 2 by 768. So that's the size of the list that we're actually looking at. Not a list, but it's actually a tensor. Let's just think of it as a list. And the first thing in the tensor, which is hello. So the word hello, when it's getting fed into the model, actually looks like this. So that's 768 numbers that we used to represent the word hello. That's what we call a vector. That represents the word hello. That's an actual embedding right here, that word that the language model is looking at, right? And anytime it's actually doing processing. So it never sees the actual word hello. This is what it sees, right? And actually now we're just doing a calculation of the model size. 124 million parameters. This is GPT-2, pretty small, coming from back in the days, back in, oh, when was it? I forget when GPT-2 was released. 2017, 2018, 2019, something like that. Right, and it just 124 million parameters. I think this is still a smaller version of a GPT-2. And that's pretty basic, and it's still gonna put a bit of stress on our GPT-2, right? On our GPU, right? On that tokenize that pod tokens. Right now we're setting up the padding token. I'm setting MLM equal false. So this means mass language modeling. So we're not doing mass language modeling, we're doing causal language modeling. So that's why we set this right here to false. Tokenizer, we put in tokenizer. And this is a function called data correlator. It actually manages how the words get processed basically during the causal language modeling. So if you wanted to do a different type of task with these words, you'd probably be using a different data correlator, depending on what you want. So you have a number of these inside the transformers library, but this is just the one that we use for causal language models. Oh yeah, this is just that same login thing again. So this we're setting up the training arguments right now. So let's go over a bunch of them. Wait a minute. Oh, I didn't get the right access. That's it. This thing. Yeah, so I just need to log in Hugging Facebook because I have this set to true. Yeah, so we need to have this right here. Let's run this one now. But let's go over some of these parameters that we're looking at, right? So output there, I just renamed this to GP2 test. So that's it right here. So anytime we run the training function, we're gonna create a run inside of this folder. And these are basically checkpoints. This is standard practice when we're doing language. Any type of machine learning. So you want to save checkpoints so that you don't have to start again from zero if anything goes wrong in the training, right? Per device training size, we have a batch size of 4. So that directly correlates to, oh, well, I guess that's probably a bit too small. Because that directly correlates to how much GPU RAM we're using, right? Can probably turn on top of it. But it's not like we're gonna sit here and actually wait for this thing to train. It can probably be bigger. You can literally just look at this number and look at this right here and get the idea of how much further up it can go. So you can probably just turn this up to 32. And again. So this thing goes up right here, so that we're using more memory, right? More GPU memory. Right? So evaluations are to the steps. That's just telling you to use steps and evaluation, even non-eval steps. So I have to do a bunch of evaluation while training. So that's just telling the number of steps you use, login steps, number of time steps to take before you actually log something. Accumulation steps. That's another computation when I do computing gradients when I want to, before you actually apply the accumulation, apply the gradients basically. But that's too deep into the weeds. Non-training epochs. We usually want to train these type of language models for a single epoch because there's so much data. We don't usually train them multiple epochs. So that's the amount of time that you go over the data, or data basically. Weight decay. So this is a regularization technique. We don't need to worry about that too much. Warm-up steps. This is kind of another similar to regularization technique I use to address it with the performance of the model. So it doesn't learn too much stuff at the start and consider it doesn't place as much importance on the earlier stuff that it learns basically. Learning rate schedule, so we're reducing the learning rate and we're setting basically this is a curve, a cosine curve that we're using to control the learning rate, right? Learning rate starts right here at 1 e to the minus 4 at 0.004. No, 0.0001. Something like that, yeah. Save steps, you know how that already. That's the number of steps you have to go before you actually save anything. FP16, so that's 14.16. So that's telling it to run at half precision. I believe this is for speeding up the model as well as reducing the amount of space that it takes up inside the GPU, right? Push the hub, this is directly related to the Hugging Face hub. We set that to true because in the future we plan to push this to the hub. Well, not really, because look at this. It's gonna take forever, right? So we're not actually gonna wait on this thing to train, but that is how you would train a causal language model with Hugging Face hub, right? And okay, yeah. Also, right here, when you're setting up the trainer, before you actually train the trainer that train, of course, we have to define the model, define the tokenizer, define the args that we created up here, right? Data correlator is actually very important, and of course, I always have the data set and the validation set, as is usual in a machine learning task, right? So boom, not going to wait on this at all. So just imagine that we finish this, guys, and pushed it to the hub, which would mean pushing it to basically a repository that you had created, right? We're not gonna do that today. We're gonna just pretend that we did that, but we're actually just going to pull in the model that was already created by Hugging Face for this course right here. So boom. So we're gonna actually use the finished model to actually generate some text to give you guys an idea of what a raw, fine-tuned model kind of looks like. So this is what we're starting, right? So notice the input text. Oh, I guess the output is already there. You guys can already start. So too bad, but yeah. So this is the input text basically, and then we have the output text right here, which is this text right here plus some extra text, right? So all it's doing, guys, again, it's just predicting the most likely next token to come, right? So it's not necessarily gonna make sense right here, but what it's doing is what you're actually trying to do, which is just predict the next most likely set of words. So X min, X max, and this kind of looks like it makes sense. Before it was trained, it wouldn't have been anything sensible. So that's what it looks like. Post training, post pre-training. And we're just gonna do the same thing here again. Generate a bunch of different code basically. So that's kind of it, guys, for training a causal language model. That's how much we're willing to go into today. Back to presentation. Where was that? Okay, here. So moving on from causal language modeling, I guess I created a timeline right here to show you guys what things look like basically over the years, right? So basically the last deep learning revolution kicked off with AlexNet back in 2013. That was a CNN, and people kind of realized that yeah, this was actually something that was going somewhere, and also this is where they started using GPUs for training CNNs basically. So everything right here is kind of CNN related. Set me off ago. So computer vision switches to neural nets. GANs are kind of generative network that predated diffusion models. Residual nets, RNNs. Well, this is not when they were invented, but I guess they were just more popular right now by this time, right? AlphaGo. Everybody should remember AlphaGo. This was big news back in 2016. The transformer architecture was released in 2017. GPT-1. Right, so it was 10 and 18. And graph neural networks. GPT-2, that's the model that we're training right now. I will just try to train. GPT-3, which is much bigger, back in 2020. Even back then, no one was expecting the quality of the output I would be getting from GPT-3. But obviously, people were seeing that these things are getting ridiculously good at what they're doing. AlphaFold 2, 2021, ChatGPT, Stable Diffusion, 2022, 2023. And I guess right now, generative AI is kind of the buzzword that we're using to name this area that we're in, right? Another thing I will have to look at is language model scaling. So essentially, what was found was that through research, people found that the most effective way of getting better performance out of the models was simply just scaling them up in terms of size and the amount of data that they put into them. But most effective, most effective than the amount of data was actually just the size, right? So you have a graph right here that shows the loss on this task of next word prediction, and it drops linearly, or it's not linearly. It isn't a linear graph, but it drops with the increase in amount of parameters that they put into the model. I think it was linear. I'm not sure about that. I have to check that. Model performance depends most strongly on scale. Yeah. The number of model parameters, the size of data set, the amount of compute used for training, right? So that's it. That's the only thing that actually matters when it comes to training transformers. Basically, the difference between GPT-2 and GPT-3 and GPT, nobody remembers GPT-1, but GPT-2 to GPT-3 was just a larger model. GPT-4 is basically the same thing, but some of the leaks suggest that using other methods like model ensembling and stuff like that, but effectively it's just the same thing. Yeah, and this is a graph kind of showing how these models increased in size over the years, right? So this is GPT-2 right here. This is actually a bigger one than we were using before. 1.5 billion parameters we're using was closer to this, was closer to GPT-1, was the smallest version of GPT-2 that we're using a while ago, right? GPT-2, 1.5 billion parameters. Llama, this is relatively new, 65 billion parameters. Then have a bunch of models in between that nobody knows about except maybe Palm. And this was before GPT-4. So nobody at the time it was 1.7 trillion parameters. And we still haven't confirmed that yet, I guess. So essentially, guys, big news, performance scales with size and input and compute, right? Fine tuning now. Before we look at the next color notebook that I have prepared, we'll have to talk about this task of fine tuning. So fine tuning is very closely linked with the term transfer learning. Transfer learning occurs when we use knowledge that was gained from solving one problem and apply it to a new but related problem, right? So first, we go to the step of pre-training, and it just predicts the next most likely token. But in this step of pre-training, theoretically, what is happening is that it's actually gathering all the knowledge that it is able to gather from that amount of text about the world, right? It's actually creating an internal vision, a model, a representation of the world that you can then use for other downstream tasks. And it actually outperforms just training on those tasks from scratch, basically, right? So just a big model, fine-tuned on, that was pre-trained and fine-tuned on a small data set gives you better results than training a relatively small model and that small data set or even a big data set, right? So scaling is really what's pulling all the weight here nowadays. So pre-trained models, so we have a diagram, so you have a pre-trained transformer, you can retrain it to do a number of different things like question answering, language generation, sentiment analysis, summarization, right? So this is the pre-trained model. We've trained it with all sorts of information from the internet. They'll call generate data. Then we fine-tune it on task-specific data. Right? And then fine-tuning. So traditionally during fine-tuning, we freeze all layers except the last layer, except the output layer, right? Because we don't want to forget. That's what we're gonna get into next catastrophic forgetting. We don't want to forget all information that we learn now. We want to actually be able to transfer the information that we learned before into this new task. We don't want it to be too specific on this new task. We kind of want it to be generalized, so we tended to do before. Freeze the early layers of the model and only fine-tune the last layer. So that's one, so you only fine-tune, you're only really training a small percentage of the parameters inside the model when you're actually doing fine-tuning, right? Not changing all the weights in the model anymore. That's only during pre-training. If we have enough data, then I guess we can fine-tune on the whole model. But that's typically not the case, especially nowadays. So catastrophic forgetting now, guys, that's when we start training the model we start fine-tuning the model and find that it's actually forgetting information that we learned earlier on. So it's actually just a failure and it's limiting the generalization of the model. So it's something that we want to avoid. Adapters. Let's talk about adapters. Adapters are kind of the in thing right now, form of parameter efficient fine tuning, right? Its method enables efficient adaptation of pre-trained language models, PLMs, to various downstream applications without fine tuning all the model's parameters. So let's continue. Fine tuning large scale PLMs is often prohibitively costly. And in this regard, PFT methods only fine tune a small number of extra model parameters, thereby greatly decreasing the computational and storage costs, right? And recent state-of-the-art PFT techniques achieve performance comparable to that of full fine-tuning. You know, sometimes these claims aren't as true, but I guess we can take that one for what it is. So let's have a look at LoRa adapters. LoRa's are just a form of fine-tuning, right? So I don't think this is a very good diagram, but this is the one that people tend to use. So these LoRa's are actually separate parameters that you add inside the layers of the model, right? You have the model, you create the model, then there's jamming some extra layers in between those layers, and you fine tune those layers. So you can avoid this problem of catastrophic forgetting because you don't ever actually retrain the whole model, basically. You want to fine tune the lower weights, and you can extract these lower weights and place them separately than the model itself. So they offer just a number of advantages, and also reduces the number of training parameters that are actually training because you're not training the whole model again. Training is much faster with LoRa. Computation requirements are lower. Train weights are much smaller, on the order of megabytes instead of the typical gigabytes that we get from an entire model. They are hot swapper. We mentioned that before, right? And the last thing that I want to get into before we look at the code is quantization, right? So quantization, basically, we're talking about floating point numbers, and essentially we want to use less numbers, because if we use less numbers, we can do less computation, right? So this is what a typical floating point number look like, FP32. That's a typical 32-bit number, and that's a number, and this right here is the number of bits that it takes, right? So basically, at the end of the day, we just want to reduce the number of numbers that we're doing calculations on, so we can reduce the amount of computations that we do, and reduce the amount of time that it takes to do it. But this is always basically a trade-off when it comes to performance. So quantization is pretty common, but it also enables smaller devices to be able to run these LLMs at a performance penalty. So this is an example of what you can do with LoRa's, right? So for image models, we haven't been talking about image models, but you know, I like to visualize things. It kind of gives you a very good idea of what you're doing with LoRa. So you're fine-tuning an image generation model on a specific task, right? So this LoRa right here, for example, will give you a consistent output when it comes to these types of 3D room images. So you can just give it a different prompt, and it always creates this type of image on the output, right? For example, another example is you want to create consistent characters. So you train it on a specific character, and it always produces that character on the output, basically. So you have the image generation model, but when you add the LoRa to it, it only does a specific task that it's trained to do. So LoRa's can sometimes improve the performance and specify exactly what you want to do with the models. That's fine-tuning again, right? So we're gonna look at the demo now of LoRa hugging face up. Right? This one. So again, this isn't my code, guys. I got this off the internet. All thanks to this guy right here. I made this available. But this is fit for purpose to what we want to do right here, which is just show you guys how the LoRa thing works. And specifically, we're not going to use the image model. We're going to use another language model again for this LoRa fine-tuning. So again, we're going through the pip install. This time we're using PEFT, parameter efficient fine-tuning. Bits and bytes. This is another one of those modules that is very useful when it comes to fine-tuning models. Transformers again, and some other stuff. Just gonna run everything. So I think this one runs quick enough. We can actually go through and see everything. So again, right here, this is very important, right? The model name. Also research lambda. This is specifically related to somewhere on Hugging Face, right? So we control C this and search Hugging Face Hub. We should get this, right? And here it is. So this is a specific model on Hugging Face Hub. And this is just us calling thing basically, right? Just pulling thing. Model name. This is the data set that we're going to train on. And if we want to learn more about the data set, versus something like this. Right? So that specific thing right there. And if we check it out, we actually find that it's a subset, 1,000 samples of the excellent Tim Detmer's Open Assistant Guanaco data set. Right? So this is a subset of another data set. Because what they found was that it would be better if you trained on a small amount of high quality data. There was I think a paper written by Facebook. You train on a small amount of high quality data, and that's better than a large amount of low quality data when it comes to fine tuning, right? So that comes from this right here, and then this comes from the original Open Assistant data set. Right? So it's a subset of a data set. So just very fine tuned, very specifically selected. Number what do you call it? Question answer type questions for the training modeling. So we're gonna train modeling modeling question answer. So these are those parameters for LoRa or mathematical stuff right here. LoRa alpha. So you just affect the performance. It can be any number. These are hyperparameters. It can be any number. You can pick the number that you want this to be. Drop out again another hyperparameter for the LoRa. Use 4-bit. So I guess they're using 4-bit precision, right? So when we talk about quantization, we're going all the way down to 4 bits. That's going to significantly reduce the quality of the model. What it will be given computation in 16, 416. And F4 again is more about quantization stuff, right? I have an output directory, number of epochs only training once, FP16, BF16. Okay, more quantization stuff. Per device training, yeah. So the training size of each batch, 16, gradient accumulation step, we saw that before. Checkpointing, max gradient, yeah. So there's a bunch of hyperparameters up here, guys. Are we finished? Actually moving quite fast on this one. Remember I said LoRa is trained relatively quickly, but it's also a far smaller amount of data that we're using. So we can actually just wait on this one. Max steps. This says -1. I have to check what it says -1. Group by length, save steps. Yeah, so we're not going to do much saving because we're only doing one single epoch. Oh wait, no, we're not going to do any saving at all. Max sequence length, it doesn't have a max sequence length, so I guess we'll just be using the default max sequence length. Fucking. Okay, yeah, I recognize this one. So this is done for efficiency to actually speed up training basically. So we group stuff together, I guess. So inputs, the separate inputs, gets grouped together so we can process stuff faster. Device map 0. Usually in PyTorch, device map 0 that refers to the GPU. So of course, loading the same data set I mentioned above, split, take out the training data set out of it. This is a Python function. Literally just learned this one recently. We'll get in, I think it was the data type we're getting from this. Yeah. Compute type. Yeah. We're getting right here and we throw everything into this bits and byte config right here. So there's a number of parameters you have to focus on learn these. Yeah, in our own time. Check GPU compatibility. I guess we checked that before. Wait, remember, we're still using the A100. We're using a decent amount of the A100 right now. 31.4 with 40 gigabytes. Automobile config. So as for this is very similar. So we're pulling a model from the pre-train. We mentioned the model name up here. I mentioned quantization config. That's a bits and bytes config. So this is integrated into the Hugging Face. Okay, guys. Great. It looks like we finished training already on this lower model. And I said, guys, these types of things, I just want to give you an introduction, but these types of things are all over the internet, very easy to access, very easy to find stuff like this on Hugging Face or anywhere else, basically, that, people upload stuff to GitHub, so you can always take a look at that. But Hugging Face is what we're talking about. Okay, so we're gonna generate some output right now. If you notice the input prompt, this is a regular language model, right? And we just fine tune it a while ago on question answer, right? So the prompt that we're inputting is what is a language model, right? We're gonna expect some kind of answer as of now. Although it's guaranteed to be a good set of answers because this was actually already trained on chat. Yeah. A decent quality answer like we're expecting. So what is a large language model? That's the input text. And we actually get a proper definition right here. A large language model is a type of artificial intelligence AI model that is trained on a large dataset of text, something, stuff, right? And it gives a whole bunch of extra stuff that you really didn't ask for, but it's there. And also, I think this was a mistake though. The model actually created more questions before I actually asked them. I didn't put in these prompts, I just created these ones as a part of it. So I think that's a flaw right here that could be fixed. And I think what they're doing right here is deleting a bunch of the stuff that we just created because of what we're going to do down here, which is reload the model basically from the Hugging Face. So on this first. So we're pulling in a model right here. Well, basically it's the same model that we just trained. And this is just something else that you can do with Hugging Face. So we can of course create the models, put them up on the Hugging Face. So sometimes you have to create these different type of access tokens. Fool around with these models. Okay? But that's basically a taste of how simple it is to do PFD. Because guys, this is the great advantage of Hugging Face and all the new libraries that are coming out today. They obscure a lot of the stuff, a lot of the boilerplate code. So you don't have to worry about a lot of stuff right here. So we're pulling a model, reload the tokenizer, and I'll push it back to the hub. Unnecessary, but we can just move on. Yeah, so next topic, guys, inference. So remember, I said the third most important thing, well, it's not exactly the most important thing, but the third thing that Hugging Face provides you is compute, which is actually one of the most important things for doing machine learning, right? If you don't have a computer, you're gonna compute, right? Inference is just a process of running data points into the model to calculate outputs. So have descriptive and predictive AI systems are primarily used to analyze and make predictions. Generative AI does a step further by creating new data similar to its training, right? So we're moving out of this, remember this, we're moving out of this stage of predictive AI systems and now we're in the stage of generative AI systems. And that's why inference is so important. We finally have a use case for actual AI that most people are willing to pay for, not just businesses. Hugging Face spaces. Okay, so I'm just gonna look at a bunch of Hugging Face spaces now. Hugging Face spaces basically just allow you to run inference on the same models that we're looking at. But before that, I think we have another way of running inference, which is directly through Collab. So we can get an idea of what inference looks like normally before we run it on Hugging Face. So this is MMS inference. This is a notebook I prepared. I think I copied some code. I remember from where. Yeah. So pulling a bunch of stuff again, quite normal stuff, torch, transformers, have a new one here, YouTube. And this is a specific version of Transformers. Oh no, this is just Transformers again. I guess I did this too many times. So what we're doing right here, guys, we're going to be downloading a song with Python directly from YouTube so that we can put it into MMS. MMS, I guess we should look into MMS first, right? MMS is a text-to-speech model, right? From Meta, Facebook. It's kind of the state of the art right now, and it has, I think, 4,000 something languages. At the largest level, it has a 4,000 something languages. But we're going to see how we're running into some problems where, yes, it's a state of the art, but state of the art isn't very state of the art either. Right now, when it comes to non-English and non-popular languages like French, English, Chinese, something like that, we call them low resource languages, and Jamaican is one of those low resource languages. So we're just pulling a song off YouTube. Specifically, this song right here, abstract at the highest level. And I specifically chose this because it obviously has a lot of Jamaican language in it. And this is the actual translation for what the song says, right? We're gonna need this for it. So okay, see that? That's it. We're gonna turn that audio. And now, you know, guys, you know, audio is just a list of numbers, right? So it's perfect for fitting inside a language model or inside a AI. Yeah, it's perfect for fitting inside it because it's just a list of numbers, and these things are just about processing numbers. So let's take a look at that. So these are the actual words of the song. That's the song itself. Just put a while ago. So we use the browser to actually load in the song after audio file or just download it. You don't have two things. You have the data itself from the song and the sampling rate. Sampling rate is actually very important when it comes to songs. Sampling rate, as it increases, you get the high quality audio basically. YouTube typically about 44,000 or 22,000 for the sampling rate. So, and that's high quality audio. Audio, you tend to have high quality audio. YouTube, I think, default to higher quality audio. So this is it. This is literally the length of the list. Audio is a single list, and this is the shape of the list. Just one single list of this amount of numbers. 3 million something. For this 2.59 seconds worth of audio. It's just a single list of digits. A floating point basically. And we can just literally just throw that inside of the Facebook MMS model. And this is the one that does the translation for Jamaican language. Yeah, we're gonna try doing that today. This is the one that does the translation for 4,000 languages. And that's the only one that actually supports Jamaican. So we're gonna test it. The smaller models don't support, as the smaller you go, less than 1 billion, you have less support and less performance basically. But also, you know, the quicker to run. This one is the best one of all of them. And we're gonna have a look right now at how it actually performs. Best in terms of actual performance, but not best in terms of output. The best in terms of output, but not best in terms of speed. So this is what we're doing for inference right now, right? We're running this on the we're running on T4. It doesn't really matter though. I guess yeah, the A100 would have been faster, but it doesn't really matter because this is I think measured on the A100, it would have taken about 6 minutes to process this 3 minutes worth of audio, right? And this is essentially output, right? So for the Jamaicans in the audience, you guys can kind of read this and kind of have an idea of what the quality of the output is, right? So compare this to this, and you kind of see it kind of manages to translate the words properly, but not really. This is actually almost gibberish. Almost gibberish. So this is the state of the art right now when it comes to Jamaican language translation from audio to text, basically. This is the best we can do. Oh wait, that's not the best we can do. This is the best we can do. All we do right here was specify the tokenizer or the model to be used in Jamaican language, right? And this is the difference in output. We still don't have time to run the inference, so we can just compare this again. But I did ahead of time. We can just compare. This is one is this is what I think default is set to English. But what we do right here is set it to specifically Jamaican because it has 4,000 language settings that you can use. But you can see right here, guys, comparing this to this. This is better than this. I don't want to give you some time to look at that. But it's still almost gibberish, guys. Still almost gibberish. So not very state of the art in terms of state of the art for speech to text as it relates to low resource languages like Jamaican, right? So that's the update on that. But we're still doing inference, so we're gonna look now back at Hugging Face and how Hugging Face does the same thing. So this is basically that same model, Meta MMS, but it's in a Hugging Face space. And it does exactly what we're doing over here, which is just run the model, get the input, get the output, right? Let's turn on the script. Or we could do a recording. We want to do a recording. I don't even remember if this fits. This fits inside of this next thing. I didn't go over much of the code for. I didn't go over much of the code for the inference, guys. I guess it's kind of getting a bit late. But it's a typical affair. One. No. Let's upload again. Use music for upload. Okay, there we go. Submit. So this is what I mean when I say Hugging Face provides compute. It's really just compute for inference. So if you want to test out a model, for example, this MMS model, you can literally just go on here and check it out. So we have, of course, we have other spaces. So we have Seamless. I think Seamless is related to MMS. It's released by Facebook as well, but I think it's fine-tuned on a number of things like audio to text, text to audio. I think that's it. We're not gonna get into Seamless today. Still waiting on this to process. Well, I guess it's also first. I don't want to end without showing this processing. Because I'm underestimating how long it will take. Oh. Well, guys, doesn't look like we're gonna get this one to process today. In this, I guess if we want to wait, but I don't think it's worth the wait because this is basically the same performance you'll be getting over here. But you just avoid all the coding when you use spaces, and that is basically Hugging Face spaces. Of course, you have spaces for everything. Everybody can build a space, but when you upload a notebook, comic factory. So if you have an image generator, stuff like that. You have the chat models in spaces, of course. So it's just running compute on the same model, like how doing it. Okay, guys. Side note on that MMS, we can't even run it, but that is the nature of deep learning models. Take a lot of compute. to produce currently very poor outputs. So guys, I guess that will be all for this presentation. Switching over back to Oshane if you're still there.
Of course I am still.
Mhm.
Can everyone hear me fine? All right. So thank you very much, Dimitri, for that
Wait, any
wonderful.
questions, guys? I didn't ask for questions.
All right, so we actually do have some questions in the chat. Just a second, let me go to it. Right. So we have a question here. What factors could potentially lead to a newer and larger model exhibiting reduced efficiency for certain tasks compared to the smaller size model? So, got that question?
Okay, so basically the state of things now is that we only really dependent on scaling. But nobody has really found a better way right now to improve these models other than scaling. So it's really more research alone and actually a completely new architecture that surpasses transformers that would have to come up with in order to actually be transformers and reduce the size and reduce the computation that we need. So we're entirely dependent on transformers for now, but in the future, hopefully researchers come with something new. Nothing yet, nothing on that front.
Well, nothing released to the public yet.
I guess. Yeah, that's right. GPT-3 has 50,000 word vocabulary, I think. That's about right.
So
No. You have to remember now. You said 60,000 words. So the vocabulary is not the same as number of words in the dictionary because we use word pieces and not actual words, right? Remember, we're looking at the word pieces. So we combine small subwords to make word pieces. So if you would actually have the word like infantile, you would have infantile as 3 separate word pieces, basically. So we can form far more than 60,000 to 50,000 words with using the word pieces. For that question.
yeah. All right. And we don't have any questions from YouTube?
No question
Great. So
from
no questions
YouTube.
from YouTube. All right. So let's move on. So as we've said before, guys, the hackathon is actually scheduled for September 23rd, and we'll be at the venue, UE, the computer lecture room. All right. And of course, you can sign up online. So there's a Google Sheet available. We'll be posting that link in the chat as well. Let me just do a quick check if Matthew, are you available to just do a quick run through? All right, so we're not hearing from Matthew. So yes, essentially the 23rd of September, we'll be having our AI hackathon. All right, so if it is that you want to brush up on your skills, feel free to run through some of our workshops. We've done, this was actually our 3rd workshop that we've done. So it would help you to, brush up on those skills. And, oh, we have Matthew joining.
All right, guys.
Hey, Matthew.
Good hackathon.
Matthew? All right. So please, of course, prepare yourself. It's a team event, the UE Hackathon on September 23rd. All right. Of course, we definitely would want to thank our sponsors for allowing us to host this event. And of course, you guys for joining. We have in the chat the link where you could actually view our past events. Second, so we have in the chat where you could view some more details on some of our past events, which include the other AI workshops, if it is that you missed it. Want to, of course, thank our speaker, Dimitri, and of course, we definitely want to give a shout out to Yui for allowing us to host the event, the Yui Hackathon, the AI Hackathon at Yui. All right. If it is that you'd want to contact us, this is our email. You can, of course, check out more information on the community at our meetup.com link here. And of course, we do also have discussions on jobs, upcoming events, areas that we have expanded or incorporated within our community activities, whether it is or physical meetup, because we actually do have physical activities that we do participate in outside of our workshops or career day or demo day, etc. So of course, please stay in contact with us and sharpen up your skills. Take as much advantage as possible of this opportunity where we get our top-notch speakers, top-notch presenters in the various fields to come and share the valid information with you guys. All right. With that said, I bid you farewell. You're right. So the link.
I just posted a link to the sign up for the hackathon.
You're right.
Yeah, the Google form.
Right. I'm seeing it in the chat. So guys, the link has been posted. Is there any other thing you'd like to mention, Matthew, before they go?
Just a great presentation. I think it was very informative. Probably one of the better presentations on LLMs I've seen in a while. So yeah, good job, Dimitri. I'm sure everyone listening got a very informative presentation today. So yeah, so it's very good. And thanks everybody for coming out to these workshops. It's a very important step in, as I said, exposing Jamaica's AI talent, and there's a lot more to come.
Okay. All right. Thank you, Matthew. All right. Well, guys, that is a wrap. Thank you all. Have a blessed day and a productive week. Blessings, guys.